Hello, everybody. Welcome to OpenCV Live. Today we have Gursimar Singh, who is one of the principal engineers at Big Vision LLC and one of the core contributors to the OpenCV Library and a Google Summer of Code mentor for OpenCV. And today we have a very exciting topic to cover. We'll show you how you can take some pictures of your room and create a 3D scene out of it, and now you have a 3D structure of your room. And after that, you can take a new picture and localize where that picture was taken from. So this, camera localization as well as 3D scene reconstruction only using images, it's going to be a fascinating topic. We'll walk you through the various processes. And, we are going to share the notebook a little later because some of the code in the notebook we are not able to share. So we will share the notebook a little later, maybe on Monday. We'll send you an email with the notebook. But before we begin this, as always, with me is Phil Nelson, who is the Director of Content and Creative at OpenCV. He produces this show. If anything goes wrong, it's his fault. Hello, Phil.
Yes, indeed. Hello out there, everybody. Welcome. It's me. It's PHI LLIP. I am your co-host with the co-most, the second banana who's second to none. I'm also your plus one and only. You know it's Mr. Nelson if you're nasty, but you can call me Phil. And I'm here to remind you a few things we do on every single episode of this here program. The first of which is a giveaway to you out there in the audience. Later on in the episode, I will be asking a trivia question, and the first person to answer that question will win the OpenCV University course of their choosing. You can see what courses are on offer by going to opencv.org/university. OpenCVU is, industrial strength courses made by people from the industry. These are not weekend courses. These are going to take you, a semester worth of work. Even if you don't win today, go check out OpenCVU. We'll talk about them a little bit later in the episode. We're also taking questions from you in the audience, so please use the Zoom Q&A button if you're watching on Zoom at the bottom of your screen. If you're not watching on Zoom, if you're watching on YouTube or Twitch or LinkedIn Live, use the chat system on those platforms. I am monitoring those, and I'll be able to bring the best ones up on screen. Just like, for example, our friend who is from New Hampshire, who chimed in earlier this morning. We'll do that for you if you have an interesting question. We've also got folks from Australia, Baja California, Iran, all around the world here at OpenCV Live. We'd love to see it. Before we get started, I want to remind you of a couple of things. First, OpenCV is a nonprofit organization that releases open source software. As such, we could not do what we do without the support of our members and partners, such as the awesome companies presented here: ARM, RunPod, Intrinsic, FutureWay, JetBrains, RoboFlow, Hackster, the official community platform of OpenCV, Seventh Sense, Google Summer of Code, OpenMV, Orbic, the British Machine Vision Association, our newest silver members, Tangram Vision, Amp Software, Intuitivo, Rerun, the Edge AI and Vision Alliance, and Big Vision, of which Gursimar, our guest today, is a member over there, a principal AI engineer over at Big Vision. Also, if your company uses OpenCV heavily, consider becoming an OpenCV member, and you can be as awesome as all of those companies. Go to opencv.org/membership. And you can find out the ways that you can support OpenCV. We've got multiple tiers of membership: gold, silver, and bronze for companies and startups of all sizes. All the information is right here on the website, opencv.org/membership. I think now we can go ahead and get started here. Doc, you want to welcome Gursimar and kick it off?
Yeah, welcome, Gursimar. And, I have already given a short introduction of Gursimar. This is the project that Gursimar is going to talk about today. This has been, we have been working on this internally at OpenCV. In fact, this is Dr. Gary Bradsky's favorite project. He has been leading this project, and Gursimar is the principal on this project. So the idea I have already mentioned. Without further ado, let's hand over the stage to Gursimar. Welcome.
Thank you, Dr. Satya, for your introduction. This topic, right, this 3D reconstruction, localization, this has been around for decades, right? This is a big decade problem. and a lot of people are trying to solve it. It's already solved in certain domains, but things are changing fast, right? That, as we know. So we'll see some exciting things today, right? So should we go ahead
Yeah, let's
with
start.
the? Okay, okay.
Yep, there's
Uh,
your screen share.
okay, so my screen is visible, right?
Yeah.
Looks great. There's
Okay,
2 of you. I love it.
okay. So yeah, so Satya has already given my introduction. I am principal AI engineer at Big Vision. I am also a member of OpenCV development team, who's primarily working on photo and DNN module. I also mentored GSOC project for OpenCV that was regarding computational photography. And overall, my area of expertise, the experience that I have been is in computation photography, 3D reconstruction, AI engineering practices, model training, optimization, and deploying products across various domains. Um, that's about me. Let's I think get started with the topic of the day. That is building the indoor metaverse. By the metaverse, we basically mean that you're able to spatially localize yourself in the scene, right? In the digital twin of the real world, right? It can be you, it can be a robot, it can be a camera which is on the wall, right? Whatever it is, with whatever is able to see things, acquire an image, we should be able to localize, right? So overall, the pipeline, or say the building blocks, there would be four, right? The input to the overall architecture would be a video clip, right? That basically could be of a room. We are focusing on indoors today. So it could be of a room, of multiple rooms, and all these things. And we take out some frames out of it, and then should be able to do a complete 3D reconstruction around it. We'll go into details on how on each step, but this is just an overview of how a 3D reconstruction looks like. And then, let's say you come the next day, you take an image by standing in the room. We should be able to tell you in that 3D reconstruction where you are standing, or what is the position of the camera which took that picture, right? So that's the overall idea of the metaverse. So basically this enables anyone which has the camera, which is seeing the view, to interact with the overall everything in the room, and open gateways for a lot of downstream applications that can be built upon it, right?
Yeah. So one
Yes.
of the
So one of the
that is
that
Gary's favorite is let's imagine that you are you have a you have a house um, and basically you take pictures of this house and develop a 3D reconstruction of the house, and then you let's say you're putting in new cameras, security cameras inside the house, and it could be a house or a an industrial space. There, without doing anything, you are able to figure out where this camera is located, right? So whether it's in the living room, etc. Not only that, the exact orientation of the camera you're able to locate, right? So this is a very difficult problem. This is a very challenging problem because in a when you're looking at the same scene, you're using two cameras, then it's easy to locate the two cameras with respect to one another. But if the space goes very large, where there is no overlapping view, then it becomes extremely difficult to say how one camera is located to situated in relation to another one. So let's say you are building a big security system for a large building. You should be able to do camera handovers and things like that using this when you have this kind of information available.
Yeah.
Okay.
Okay, so this is again the similar pipeline which we talked about. Video clip is the input, then we do the 3D reconstruction, then we move on to the localization part, and which we get a camera pose. In the end, we'll also see some cool visualization techniques that we can use to show the predicted camera pose as well. So This problem statement, as I said before, has been there for a couple of decades. People have been, and there are some very strong classical techniques which are available, that people use. Right. The overall goal is to localize the single camera image within a point cloud of a large room, and we want to ensure high accuracy, fast inference, and no dependence on any other sensor data. It could be IMU data, it could be LiDAR data, and other sensor data. We just want to do it with a single image, right? So even if you take a picture from your iPhone, or if you take a picture from an embedded camera, or a camera on a smaller chip, right, it should also work. Um, and why not SFM? So SFM is one of the classical techniques, or the theoretical techniques to do 3D reconstruction from a set of input frames. Why not use SFM? Because existing pipelines basically combines multiple modules, but often fail to achieve high accuracy and robustness. Right. So 3D reconstruction fundamentally involves detecting key points in across multiple frames, which are similar or common to each other, right? And then you can theoretically, which we'll also go through, use something called triangulation to determine the 3D position in a global space, right? So that's the fundamental of 3D reconstruction. So SFM does that, but it has multiple building blocks, like key point detection will be done via another algorithm. Then you do bundle adjustment, a complete pipeline, right? So the robustness is a major challenge over there. One I say the strong library which is still used a lot is something called OrbSlam 3. Again, with just visual data, OrbSlam 3 is not very robust, but it works very well with IMU data. And let's say if you have depth data using LiDAR, this work very well, right? So, and one thing different in SLAM is that the mapping or the localization that you are doing is simultaneous, right? So while you are creating the reconstruction, at the same point you are doing the localization as well. So that is mostly used for in robotics, right? Today what we are focusing on is you do the 3D reconstruction first, and then once the reconstruction is done, then you can localize, right? So it's like you do a scan of the complete room first, and then you can put any robot or anything in that environment, and then do the localization, right? Then advancements with the deep learning, some deep learning methods also tend to solve the camera localization problem. One of them is something called A0, which we have worked a lot with. It provides very good results, very reasonable results, but it still fails on larger rooms, all right, or large number of images. So if you have like an auditorium where you want to use it, the localization still fails, right? So that were some of the drawbacks which kept us working on this problem furthermore and trying to solve it.
Right. So just to recap a little bit, actually it's on this slide you can see. Um, so structure from motion in traditional structure from motion, usually you take several pictures of the scene. Let's say a room, you take several pictures of the scene, and you usually have the camera parameters, right? How the cameras are located with respect to each other, and you do the very first thing you do is for every image that you have captured. You identify features, right? Features could be corners and things like that, which are stable, and which can be matched across different frames. So it is a sparse set of features. Let's say you could identify 100 features in 2 frames. For simplicity, let's just consider 2 frames. So you would identify 100 features in this, 100 features in that, and try to match. Some of those features will match. Let's say 70 of them match, and using those 70 features, you are able to locate. You are able to triangulate those points, right? Just like you have seen that if we say that this point is visible in this location on the first camera, and on the other camera you're seeing the same point at a different location, you're able to use the triangulation, right? Simple geometry to say what is its location in 3D. And this you do for all the feature points. And then there is another step called bundle adjustment, right? In bundle adjustment, you basically try to also rectify for camera positions, etc., so that you get a better match. So once you have done these, you then do a dense correspondence. So these were only for a sparse set of features. Then you do a dense correspondence to figure out what should be the depth map, and you can get a dense set of points, right? You may not get a dense for every pixel. You may not get the results, but you'll get a dense 3D point cloud. So that's structure from motion. Slam, it is solving a similar problem, but you do not have information about the camera positions. So it is simultaneously doing localization, which means that where is the camera located, and mapping, creating the 3D structure, right? And Orb Slam 3 is it's the most popular, I think, method in this class. It also uses IMU data, right? Inertial units, so that you know that what is the orientation of the camera. Even if it is a rough orientation, all the cell phones, for example, have that information. It is able to use that to do simultaneous localization and mapping, right? So that's the classical methods, so to speak, right? And
Yeah.
Gursimar, you could cover the other ones.
Yeah. So then, so from the classical one, right, as we progressed with deep learning and AI, right. So as Satya talked about the feature matching, right. So if you have two images and you identify 100 features in both and try to match 70, the definition of that feature in classical way would be like an or feature or a shift feature or surf feature, right, which are basically corners and some descriptors for those corners, right. So in when we try to do it in deep learning, models like superpoint, superglue came into existence, which are deep learning based key point detections. So it identifies a point, and the descriptor is basically a vector or an embedding generated by a deep learning model, right? And superglue is again a deep learning matcher, which is basically telling you which two vectors are similar to each other, right? Imagine if you don't have superglue, you will be doing something like a Euclidean or a cosine distance to match if these two vectors are close to each other. But superglue is trained on descriptors of superpoint to say that these two features are the same, right? And then build upon these deep learning feature matcher and detectors, something called master also became very popular, which again used deep learning for dense correspondence. So this again is built on modules, blocks. One block is doing the point detection, feature matching, and the other block is doing the SFM and then the dense reconstruction, right? So overall results of master as well are pretty good in general. Um, One thing, it takes a lot of time, definitely, but again, it might struggle with robustness, right? But master was one of the kind of a breakthrough in the deep learning reconstruction algorithms, right? So next, coming up to the what is the latest state of the art, which is the what is the latest and the greatest. So these early models often come with high computational cost, also while still struggling with robustness. So robustness is a major issue in this is domain, right? Because sometimes you might land into environments where you don't get enough features, right? So imagine you are just there is a long scene where there is a wall, right, a blank wall. There are not enough features, unique features that you can match and then identify in a unique way across frames, right? So this paved the way for a more efficient, more complete architecture, something which is called VGGT. VGGT released by Meta, right? Visual Geometry Grounded Transformer. It's a single end-to-end model that outputs 3D point clouds, depth maps, camera poses, and cross-frame key point matches, right? So when we say a single end-to-end model, why that is good and a kind of a breakthrough is because there is a single neural network which is taking hundreds of images or maybe less than hundreds of images, right? Even a single image, and is able to give you the depth, the point cloud, the camera pose of all the input frames, and also what are the key point matches across frames. I'll show you the visualization. So this is like the left hand side is the sequence of input frames. The middle one will show you a 3D reconstruction, and this is basically the camera poses that show you from where the image was taken. On the right hand side, you can see like between two images there are straight lines, which shows you what are the key point matches across the frames, and also the depth, right? So these are some of the fundamental things that you need in any 3D reconstruction problem, right?
Yeah.
Uh, Till this, there were models, state of the models for each of these different domains, right? Everyone was solving different domains and trying to get the best out of it. And what you will do is try to then piece together this complete pipeline, taking state of the art in each of these building blocks, and then getting the final reconstruction out of it. But VGGT, just a single, you can imagine a single PyTorch model giving the images as an input, and you get all these things and outputs. It is opens ways to like a backbone, right? Which can you can now build more models around it, right? So if I have to give analogy, it will be like we have in traditional sense classification models, right? CNN based classification models, right? So what happened there is that you have the same backbone, let's say a mobile net, and you can uh, train it for classification, detection, segmentation, and other tasks, right? So the backbone remained the same, and then the head changed based on the task, right? So uh, I imagine in the coming years it would be something similar over here in this domain as well, that this becomes a backbone, and then you have multiple heads doing different accomplishing different tasks in a single model, right? And which is end-to-end trainable.
Right. One other interesting piece, I just wanted to mention is VGG. Actually, this paper is in collaboration with the Visual Geometry Group as well as Meta, right? So uh, the VGG, they have very cleverly used this, because actually VGG stands for Visual Geometry Group, right, at Oxford. But here it is called Visual Geometry Grounded Transformer, right? So the VGG still is there. And also, people may have heard about VGG net, which was used for as a backbone for, classification networks, etc. That also came from the same group, right, from the same university, the VGG group. So it's kind of clever that they
Yeah,
called it grounded transformer.
right, right. And it also gives us the complete feel, right? What's the VGG from the VGG net also gives us the feel that
Yeah.
it can be used as a backbone in future, right?
And the one other thing is that if you look at the outputs it's producing, right, it's producing the camera positions. Yeah. So it's producing these camera positions, as well as the depth map, the point cloud, and the tracks, right? So it's producing more than necessary, in the sense that you could argue that once you have the point cloud, you don't need the depth map. You can calculate the depth map from the point cloud, right? Yet they found out that it is actually a good idea, right? It makes the solution more robust if all these outputs, there is redundancy in the output, and they found that it actually produces better results when you output all of these different things, right, and not just the minimal set.
Right, right. Yeah, and what changed over here as well is that why it became like it is very generalized and very robust, because the backbone of everything there is they are using a transformer models, right? So, and as we know, with large amounts of data, you can actually scale it to up to maybe a billion parameters also, right? So the like VGT is, I think, the first billion parameter model in this domain, right? Which has the capability of becoming like a foundational model, right? So it unlocks that as well. So I'll show you some of the. So this is the project page, right? I'll show you some of the outputs, right, from them, which they have only provided. So this one, which is on the screen right now, this is like a again a 3D reconstruction of the
Amphitheater.
amphitheater. Over here, this is the image,
So
And
this
this is a
is
single image.
this
Yeah.
is working on a single image, right? So that is another interesting thing, that this algorithm works on single image, two images, as well as multiple images. Uh, we are not seeing the.
It's loading. Yeah.
Okay, okay, okay. Yeah. So using those images, it creates this 3D cloud, right?
Yeah.
You can point cloud.
So like the input images you can see over here, right?
Yeah,
And this looks pretty good, right?
yeah,
The structure is maintained. There are some level of details as well. And like for the now you, because you have also have the depth map, you have also the key point matches. Even if you want to make it more dense, even if you want to add like photorealism to it using Gaussian splat, that is all doable, right?
yeah.
So all the information that you need is there from this model, right? So this is again another example of an indoor using a single image, right? So
That's
imagine you have the RGB data from the single image, you have the depth, and you can just do this.
that's amazing.
Yeah. So they have shown also comparison across like different methods, like Duster or Master was one of their like improved version on Duster, and then something called Faster, which is like a faster version. But still, you can see the difference in the reconstruction quality, right? You can see the artifacts in case of Duster, and in case of VGGT, the
Right.
overall difference. Right. This is from two images. The two images are
Well,
over
that's
here.
that's also fascinating. Look at those two images; they don't have any overlap, right? So it's not very clear here. I think these two images have almost, they have zero overlap, right? Do they have any overlap?
There is small overlap, I guess,
Small
at the
overlap.
bottom.
Yeah. Okay.
Yeah, so, maybe not that as well. Also,
Yeah.
yeah,
It's kind of confusing to know where these two images are taken from, right?
right,
For humans also, but it is able to do a solid reconstruction with just two images with almost negligible overlap.
right.
Yeah.
And they show the generalizing capability as well by doing it on not a real image but a painting,
Mm.
right? So they show that on even a painting, this like this is a flat. In Duster, you're just getting a flat output,
Right.
right? In Faster, you still see some depth, but it's not accurate, right? But over here, right, you still have that 3D component to it.
Right.
So overall, the outputs are great. The overall generalizability is great, and it is trainable, right? So someone wants to fine tune this maybe on their own data in their own domain. That is also doable, right? So that does is not the case with maybe a classical method or other methods in this domain, right? You need to train each of the building blocks separately, but there's an end-to-end pipeline available that is trainable as well, right?
Yeah.
So, coming back to the topic of today, right? If we look at the complete pipeline again, giving you a recap is the first step is 3D reconstruction, and then we want to do a localization, and then we will move ahead to the visualization part of it, where we'll show that when we have extracted the camera pose, how do we know it is correct? Right. So camera pose is just a metrics that we get, but how do we know it is correct or not? Right. What does it exactly represent? So 3D reconstruction from VGGT, I think we have gone over this for now. Coming to some of the technical details or the practical details out of it, it takes a handful of frames. The more frames we provide, the denser and more complete the reconstruction becomes. So it works with single frame as well. It works with 10 frames as well, but there is no upper limit, right? And the more you provide, the better it is, right? So the more overlap you give between images, the better output you will get. Obviously there is a saturation point, right? If there is, it might not need that much overlap in a lot of cases, right? So but that opens up the point that you can do larger even outdoor scenes, as we have seen on their project page as well, right? That you don't need you can, it's not only for indoors, right? Even if you are doing an auditorium, maybe with 100, 200 or 300 images, the reconstruction is still possible. I'll show you an example of this reconstruction over here. These are, we have stitched two rooms together. We'll using these as an example throughout our um, talk today, right? And what we have done over here is this, in this reconstruction we have done two rooms separately, like room one was done separately and then room two was done separately, and then we have tried to attach them together, right? So why we have done that is because there is training at the training point, it requires a lot of RAM computation, right?
Is it
Because
RAM or GPU memory?
GPU memory,
Okay.
right? So VRAM
Yeah.
computation, and this is like a foundational model. I am pretty sure in the coming time we'll have faster versions of this. We already have a fast VGGT, which I'll show you a comparison as well between these. But like a 150 frames takes around 32 GB of GPU memory for the reconstruction part. The inference part is doesn't take a lot of memory. But the reconstruction takes 150 frames, 32 GB GPU of GPU memory, and 60 minutes of reconstruction time for reconstruction, right? But the good news is that you need to do it only once, right? So this is like a one-time process that you do need to do of the scene, and then you can just localize anything and everything in that scene, right? And this, so because that is there, and because 150 frames we can only do one room with the highest level of accuracy that we wanted to achieve. So that's why we did it twice, like in separate in a sequential manner, and then we'll also go through the scene alignment, how we solved it, so that we can expand it to like complete floor of a house or of a building, right?
Right. And even if we had, even if this took less memory, right, there is always the scalability problem, right? At some point you will need to scale, right? What about 5 rooms, 6 rooms, etc.? So there has to be a mechanism where you're stitching these 3D reconstructed scenes together, uh, so that it becomes infinitely scalable.
Yeah. Yeah. So from a product perspective, in the end, we have to go into some stitching, right? So just recap on the outputs of VGGT. One is the point cloud. This I think we have already seen. Then it's the depth maps. These are some of two example images of the same room for which we were seeing the reconstruction. Then this is the key point matches between the training frames. So like this is the, it would have found more matches, but we are only showing the few after doing ransack, right, which basically eliminates any outliers or anything that's not very strong. And if you can see this edge, right, this is a very interesting output. This edge,
Mm,
it's very similar, right? The complete edge is almost exactly the same, but it still picked it up, right,
right.
nicely. These are the camera poses that also we get from VGT. This is a cooler visualization, which also show you at the end how we do it, how we get it there, right? So the 3D reconstruction, I think once that is coming from VGGT, right, uh, from that model, and we have seen and we have talked about it a lot. Now, when we want to do the camera localization, that part, that piece of code is not part of the VGGT repo, right? And that we need to basically add to it, right? So that is the like overall code that we wrote on our own to accomplish this pose localization, right? So this is something custom. So for this, we will go through, we'll start from the core principle of camera pose localization and then give you a complete walkthrough of the overall pipeline algorithm that can be used to do this camera pose localization from a novel view, right? So this is like coming into the domain that a downstream application we are trying to build, taking VGT as a backbone, which has given us all the raw data, right? So this is like an example of that. So coming to pose estimation, what do we need, right, for a 3D estimating the 3D pose of a camera of an image? What do we actually need, right? The first thing we need is 2D coordinates of some points in the image. So these are, we can say, the key points or the features, right, which we have detected. We need the 2D key points, 2D coordinates of these key points, and then we also need the corresponding 3D coordinates in the world coordinate system. So we have the 3D reconstruction already from this model. We need to know, right, from the query image, if I detect 4 points, where are these 4 points in the 3D as well. On the right side, you can see a kind of an example, like on this face, we have like some key points, the facial key points. We want to know where are these key points exactly in this 3D, in the 3D domain of a face, right? So similar, if we come to the room, that's like the principal input that we need. Other thing we need to know is also the intrinsic parameters of the camera. That is basically the focal length, camera center, and distortion parameters and all those things, right? So this is something called intrinsic camera metrics. And one interesting thing about VGGT is also that we don't need to give that also as an input to VGGT when we do the reconstruction. There is a module in it that does that as well, right? So that is also something that even if you have images or you just have a video but you don't know from which camera it was taken, that is also fine, right? Because it can estimate focal length on its own from the images as well, right?
Yeah.
So camera pose.
Before we get a letter from someone, I would like to state for the record that the estate of Marlon Brando is not involved with OpenCV.
Right. I think this is this image is from Learn OpenCV blog, and I must have searched for uh, you know uh, for
I just
images which
assumed
do
you
not
were a
have a
big.
license.
I
It
just
do not.
assumed you were a big fan of Apocalypse Now,
Oh, and
or a streetcar named Desire, for example.
yeah. Oh, that one was amazing. I'm the Godfather.
Carry on, Gursimar.
Yeah. Okay, so what we want to know is the camera pose. Camera pose is a combination of a rotation and a translation matrix. In theory, it is always mostly represented as like this R and T, which is basically also called like an extrinsic camera matrix, which is telling you about the pose or the location of the camera, right? So, in coming to the theory of coordinate systems, or how does an image is formed, is that if you want to represent, if you know a point P in the world coordinate system, which is represented by UVW, and you want to know from the camera coordinate system, right? So there are two frames, two coordinate system there can be. One origin could be the world coordinate system, so might be an origin on the floor in the room. That could be an origin of the world coordinate system. And from the camera perspective, right, when you look at from the camera perspective, you need to shift the origin, right? So if we know the pose of the camera or the rotation and translation of the camera, right, a point P in the camera coordinate system can be represented as a multiplication of the camera matrix with the coordinates, 3D coordinates of the same point in the world coordinate system, right? So that is what the equation one shows. XYZ is equal to RT UVW, right? So that's like a simple 3D transformation from concepts of computer graphics as well, right? And then coming to the introducing the 2D part of it into it. So the same pixel. So here you can see, right, the camera is located here, and it is observing a point P. The projection of that point P will be on an image plane, the image that has been taken. So if you want to represent the projection of that point on the image, we'll represent with small xy. So xy in that image plane is basically represented as S, which is a scale factor multiplied by the intrinsic camera matrix, which includes the focal length and the camera centers, multiplied by the uh, position of that point in the camera coordinate system, right? So that's how an image is basically formed. Each pixel, it can be represented in this equation, right? So from these two equations, like we know, if we know the 2D points, the small xy, we know the fx, fy, the intrinsic camera matrix. We don't know the capital XYZ, which is the because we don't know the camera pose in this case. So we don't know the XYZ in the camera coordinate system, but we do know the UVW from the 3D reconstruction, right? So there is basically, if we know RNT, then we also know XYZ. And if from these two equations, basically you can formulate this into an optimization problem and solve for the camera pose that is RNT, right? So if you have in nutshell a 2D to 3D correspondence, n number, like maybe minimum of an 8 2D to 3D correspondences of a given image, right? You can solve for the camera pose using classical mathematics, right? This is just like mathematics and optimization problem. But what we need to find out is the correspondence between 2D and 3D in that query image, right?
Right. Yeah.
Which
So just to recap, one for people who may not be familiar with, if you can go back, basically there are two things here, right? One is the camera intrinsic matrix, which you see in the equation below, where it says fx, fy, and one, and then cx, cy. So fx, fy is basically these are it's the focal length in x and y direction, and cx, cy, this is basically the center, right? Uh, yeah, so it's cx, cy, basically these are the coordinates of the center of the image. So that's the camera matrix, right? That's the intrinsic camera matrix because it depends on what the camera, it's the intrinsic parameters of the camera. And then we have extrinsic camera parameters, which are basically the rotation, which you see R over there, and the translation vector. So rotation is a matrix, it's a 3 by 3 matrix, and rotation is in this case, it would be a 4 by 4 matrix, and the translation would be a vector, right? So basically this gives us the orientation of the camera with respect to the world coordinate system, right? So in our room, there are multiple camera locations that we want to estimate. So the room is a fixed coordinate system. With respect to the room's coordinate system, where is this camera located? And if we can find the rotation and translation, we are done, right? So that is what camera pose actually means.
Yeah.
Yeah. Okay.
Okay, so then basically what we need to do is, if we have the 2D 3D pairs, we have seen that we will be able to localize the camera pose using just classical mathematics. So that is what we want to find, and that is the pipeline that we need to create, right? So let's assume we used 150 frames in the VGG training, and we have all the outputs for these frames. Recapping on the outputs, we definitely have the key point matches across the training frames, right? So we also have the 2D to 3D. We have the 2D to 3D matches for at least the training frames that were part of the training. We don't have it for the query image, but we do have it for the 150 frames that we used in training. All the key points that were detected, a corresponding 3D point is known at this point, right? So then the first step that becomes is that, given a query image, I want to find what are the top K images that are similar to this query image, right? Why we want to do this is because in this case, it's just 150 image, but this could also be 1,000 images, right? And when you give out a query image, I don't want to search across, like, I don't want to find the same key points across 1,000 frames to get the correspondences, right? I can localize this problem or optimize this problem by only reducing my search space, right? So the first step that we do is that we find what are the most similar images to the input image, right? So if, for example, there is no use of searching for a match between key points, but with the query image of one room with the other room, right? Because there will be no match, right? That we know of, definitely know of. And even in the same room, there might be a view which there are no common points with the query image, right? So we want to optimize this problem. We just want to find out the similar images for my query image, right? So for that, what we use, there can be many methods to do this. What we use is a very lightweight method, which we basically call hashing. It can be called as hashing, where we generate a unique vector for each image using a discrete cosine transform. We can use a DCT function that is available in OpenCV, and then normalize it, right? So for each, let's say I have done this and cached it for all the 150 frames that were in training, right? So I don't need to do it every step. So for the 150 frame, this is already computed, this vector is already computed, which can be considered as a unique representation of that image. And then when a query image comes, I quickly compute this DCT vector, and then do a cosine, compute the cosine distances, and then retrieve the drop k. The k could be 3, it could be 5, it depends on the application, on the environment that you are deploying it on. Right. So that's the first step. The output of the first step is basically 3 frames from the training set that are very similar, or that will definitely have matches to our query image. Right. So at the second step, what we do is we run a lightweight, robust feature detector. It could be any feature detector that we have talked about at the start of the talk as well. Over here, we use something like alight plus superpoint. So we used both, and then we can use light glue as a matcher. We can even just use cosine distances on these output features to find the 2D key point matches between the query image and the retrieved frames. So the 3 frames that I retrieved in the last step, what I'll do is I'll run a separate key point feature detector on these 4 images and try to find the matches, right? So like in this example, it find a very good match on the center cardboard that was kept in this room, right? So once we know the 2D, so this correspondences which we have found right now is between 2D and 2D, right? So until now, there is no involvement of 3D in this process, right? So we get there are 2D correspondences first between query and training frames, and then we also have a complete 3D. We have a complete map where you give a 2D image and you get a 3D point as well, which came from VGGT, right? The reconstructed point cloud. So for all the training images. So what we will do is that I found that these, let's say 100 points are a match. I definitely know that in my 3D reconstruction, I have these points as well over there, right? It might not be very dense reconstruction, but definitely maybe 10, at least 10 out of these 100 will be there in my 3D reconstruction. So that means that for at least 10 out of these 100 points, I will definitely know what is the 3D corresponding point, right? Or 3D point in the point cloud. So once I know that, basically you know the 2D to 3D pairs for your query image as well, right? Before this step, you only knew the pairs for the training part. Now for the query image as well, after this step, you have at least some points where you can find out the 2D to 3D pair, right? So that is what we needed, and once we have it, we can use the same mathematics that we discussed the slides before this, and solve it as an optimization problem. To practically use it, we can use the OpenCV solve PNP function, which comes with ransack as well. So solve PNP ransack, which can be used. The input to it is basically the 3D set of 3D points, the corresponding 2D points for my query image. K is the camera metrics, which is the intrinsic camera metrics consisting of focal length and optical center. And then you can also compute something called a reprojection error, which will tell you that how accurate are you in your estimation, right? So OpenCV, like the solve PNP internally uses this algorithm. Interested people can check this out. This is the algorithm, like this is a generic optimization algorithm which is adapted in a lot of OpenCV or CV tasks in this domain. So in a nutshell, this is the complete pipeline as a flowchart. This block is completely separate, needs to be done only once. This is a training block where you take the input frames run VGGT and store the 2D to 3D correspondences out of it, right? Then you come with a query image, do the candidate retrieval first, find out the top 5 frames, run a separate feature detection and matching on these frames, on these the training frame and the query image. You have the 2D matches. You lift these 2D matches to 3D by finding the closest correspondences in the 3D reconstruction that we had from VGGT. And then you run a pose estimation algorithm using PNP plus ransack to retrieve the final pose. Right. So again, this is like a top an application built upon on VGGT. The backbone, the everything, the information came from VGGT itself. Right. Yeah. Satya, do you want to add anything up to this?
No, I think we're good. I think we're good.
Okay. So the next part, we want to see now some results, right? We have talked about all the theory of all the flow and everything. We want to see the results. The camera pose I have now, right, which is basically just a rotation and translation metrics, a combined rotation translation metrics. But how do I know as a user if that is correct or not? Right. One way is that I need to know the ground truth, right? So if you are using a very complex system with known camera positions, over there you know the ground truth, right? But in if I am carrying an iPhone and roaming around, I don't know the ground truth, right? So how do I know my prediction is correct, right? So we figured out a way to do it. An interesting way to do it is that what we will do is on the training, the same training video, we will also train a Gaussian splatting, right? So Gaussian splatting is generates photorealistic reconstruction, I'll say, of the same input video, and it is also great at generating novel views given a camera pose, right? So if I have a camera pose of the same room on which the Gaussian splatting has been trained on, it can generate an image and give me that, right? So in order to evaluate the accuracy, what we can do is we can generate the novel view using our prediction of the camera pose and then compare it against the input image for which we wanted to get the pose of. If the input image and the reconstructed image from Gaussian splat match, that means the prediction is very accurate, right?
Yeah.
Obviously, when we do this, the query frames that we use, these are not part of the training images that we use for the VGGT, right, or the G-splat. So this is one example. So if you do it for, let's say 100 images or 200 images, you can create a video out of it. And that is what we have done over here to basically evaluate. Let me go to the first example. Yeah. Evaluate the overall quality. So left hand side in this video is the input image, the query image that we gave in our pipeline, and right hand side is the reconstructed view from gsplat, and the camera pose used in that reconstruction was predicted by our pipeline, right? So this is just for visualization purposes and to evaluate the accuracy, and we can see that almost the left hand and right hand side, the view is almost the same, right?
And also note, I mean, the camera is really whipping around here. This is not a slow mo capture. Like you
Yeah.
slowed it down by 50%, and it's still pretty fast.
Right.
Yeah. So this is not a continuous video. It is like a set of frames which have been stitched together to just evaluate the overall thing, right? And if when it's fast, even if there is a disturbance, if there is some error, you will see it easily as well, because in each view there is a vast difference between each frame. In this example, then also again someone can say that if you keep the scene exactly same, definitely you will get good outputs. But in a practical scenario, objects inside the room can move as well, right? So what experiment we also did, what if we change the lighting of the room, we move some objects around, or not the bigger objects but a lot of objects we moved around in the same room, and then try to infer with that as well and try to test the robustness of this pipeline, and this came out to be pretty accurate, right? As you can see, like in the training, when we did the VGG training, there were some markers like this on the walls, on the floors, right, which were not then present when we did the testing, right? So we removed them, but you still see them in the reconstruction of gsplat. That shows that in the training these objects were there, but these objects are not present in the testing. Still, the if we focus only on the alignment of the camera pose, this is still pretty accurate,
Yeah.
right? So this is like a robustness test on this as well. So some objects have been moved around, on this seating, some objects on the cardboard in the center that have also been changed. I'll slow it down again for everyone. And the viewpoint is almost exactly the same, right? It's almost perfect, the viewpoint, right? So as you can see on the in the seat as well, if I pause it, the objects have moved up, right? This is not there anymore. There is something, some papers on the checkerboard as well, right? But it still works. So even if you want more robustness, you can, this shows that even if you want more robustness, you can have some markers in the scene while you are scanning the room, but these are not necessary at runtime.
As long as it is not completely, flat, empty space.
Yeah, there needs to be some features, right? That is still a basic requirement in 3D. You still need to have some features. It can be like 4 plain walls and a plain floor.
Right.
um, it might still do some reconstruction there, which might be useful for some applications, but not completely, definitely.
Right.
So as we talked about VGGT, we talked about that the training time is around 60 minutes, and it takes like 30 complete 32 GB memory and still can fit only 150 frames, right? And we talked about that in coming future there will be faster version of it, right? So in our experiments, the VGGT pipeline, if we used from the directly from the repo, it takes around 70 to 75 minutes for 150 frames. We were able to optimize some parts of that code uh, in the open source and brought it down to 60 minutes. And that is what we have shown here. Like for 160 frames, it takes 60 minutes of training time, and the inference pipeline that we talked about completely takes around 270 milliseconds for 1 frame. This also, there is a lot of scope optimization there as well, and we are also trying to do it on Jetson and see what kind of times we see, right? And then, but fast VGGT is also a recent release built upon this VGGT complete module. This is from a third party, MyStorm is their name of their repo. The group name is like Media Analytics and Computing Laboratory and Autolab, their collaboration. So they have optimized the training time and the GPU utilization of VGGT as well. The training time in our testing reduced from 60 minutes to 20 minutes, and then also we were able to like fit 450 frames in the same GPU memory, right? So that's like almost 3 times the frames we were able to fit in the same GPU memory. So that basically enables, like on even a smaller GPU memory, you can do the trainings and reconstructions as well.
Right.
So when we were seeing the results, we were also talking about seeing that what we did in our use case was that we stitched 2 rooms. We reconstructed 2 rooms separately and then stitched them together, right? So I thought we will talk little touch base upon that as well, right? So basically, to stitch 2 scenes, 2 3D scenes together, what we need is basically an alignment between two. We need to know um, uh, we need to have a marker or a known location uh, which is reference to both of these 3D environments, right? Which can act as a correspondence between 2 different environments, and using that we can align, right? So in our use case, we what we do is we just put 2 Aruko markers during the reconstruction time. We put 2 Aruko markers in the scene on the floor. We know the distance between these 2 markers, and we also, let's say, know them in a floor map or a rough floor map of the scene, right? So if like this is the uh, my scene and this is my floor map, these are like two of my Aruko markers in this room and 2 Aruko markers in the other room, and I know the relative transform between these 2 Aruko markers. So I have a reference. Using this, I have a reference between these two separate 3D reconstructions, right? So once we have that, we can use them to set a new origin. We can use them to transform all the points in the 3D reconstruction to a common region, right? So all the poses, camera poses, all the point clouds, everything gets transformed to this new region, which we can define based on these Aruko markers. And the purpose of using Aruko marker is that you have algorithms that you can use to just detect them in an image or a video, right, robustly. So that helps us stitch these two scenes, and using these just two Aruko markers, we experimented in our use case, and it worked pretty well. This is the kind of a video of that reconstruction after stitching these two rooms separately, right? And I'll also show you this in the collab notebook that we have, which we'll be releasing after some time. Yeah.
Yeah, and we'll make sure we share this notebook when it's available with folks in the OpenCV newsletter. You can go to opencv.org to sign up for that. Make sure you're one of the first to know.
Yeah. So this is like the 3D environment that gets built out of it, and over here we can also show like the camera poses that are part of it, that we are localizing the position of that in the 3D, and the complete. If you want to stitch it, then the stitched 3D also looks like this, right? And also to verify if the stitching is correct or not, one easy way is to like just take the z-axis and project it along the z-axis, like all the 3D points. If you project it along the z-axis, you will see a close resemblance between the layout in this image and the floor plan, that is the actual floor plan of the scene, right? So if there is the complete resemblance shows that the stitching worked also pretty well, right? And then you can also, if you want to show the output of your camera frames along with the input image, you can show like the position in this projected image as well, right? Projected along the z-axis. This is for, let's say, separate rooms, and this is for the merged scene as well. So everything then comes to a common region, and in any room you are, you give an image, and then you can localize across the floor map, right? You can show it on the floor map as well, because we know the scale between the 3D point cloud and the floor map, because we are deciding that using the Aruko markers. And then even a cooler visualization, if you want, you can create kind of a mesh or a 3D reconstruction just from the floor map, which is the rough reconstruction of the walls, and then you can use 3D elements to show that in this way as well, right? So these are various ways to basically visualize this in an application, in a product that you might build using this technology, right? And this floor map to 3D, I think, was one of our previous webinars. So
Yeah.
code for that is also available, right? So this from floor map to coming to this kind of a view synthesis. Yeah, I think that's about it from my side that I wanted to cover today.
Perfect.
Well, awesome. Thanks so much for that. We'll go ahead and I love this effect.
Let's.
All right. Yeah. Hey, everybody. Let me go ahead and bring myself back from the void, and I'll also bring Dr. Malik back here. Yeah. So that was a lot of fun and some really cool visualizations there. We have a ton of questions from folks out there, but first, I think it is time for us to do our trivia giveaway. I'm going to go
Yeah.
ahead and pop myself full screen here. If you need a reminder, one of the things we do on this show is a giveaway to you out there in the audience. I'm about to ask a trivia question based on today's presentation, and the first person to answer that trivia question correctly in the chat, wherever you're watching, whether it's Zoom, Twitch, YouTube, LinkedIn, will win the OpenCV University course of their choosing. Before we get to that, though, I'd like to talk briefly about today's episode's sponsor. Today's episode is brought to you by the OpenCV members at Intrinsic. Intrinsic creates accessible, intelligent robotics. The team is building a platform for the next generation of intelligent automation, making it easier for developers and businesses to unlock the value of robotics. Satya, can you talk a little bit about how awesome it was to work with Intrinsic for the recent OpenCV bin picking challenge competition?
Yeah, so we had this amazing competition last year. It was presented at CVPR also. This is a top conference in computer vision, and we had about $60,000 in prizes, and it it required, usually when we do challenges, we have a software only challenge, right? But in this case, we evaluated it on a real robot. So people built bin picking solution where given images, they would estimate the orientation of different industrial parts, and then the robot would go and pick it up. So the final evaluation was done on a real robot, and so it was a lot of fun. And Intrinsic, those guys are really good to work with. Uh, it was an amazing experience, right? The level of effort that they put in from their side, to bring this together, it was just amazing. And the team it's world class. Obviously, it is Intrinsic, a Google company, but we really loved working with them.
Yeah, not just some of the most knowledgeable people I think I've ever worked with in their field, but also just a really great group of folks. So yeah, go check out Intrinsic if you have robotics automation needs. They're fantastic. OpenCV is also brought to you by our friends, the sponsors on GitHub. You can sponsor OpenCV on GitHub by going to github.com/sponsors/OpenCV. It's $9 a month, or whatever you got. If you don't have $9 a month, I think you can lower that thing to be a little bit less. Quick shout out to all 13 of our current sponsors. We've got Philip Payne, Yumiko, Live Peer, RoboFlow, DJ Greenwood, iPop, Comet ML, Jonas Heinle, Alexander Ismailov, Tala Hussein, Nick Libertini, Blue Jay, and Ritus Laboratories. Thank you so much for your support. We really do appreciate that. As I said before, today's episode, the prize is an OpenCV University course of your choosing. Even if you don't win today, go check out OpenCV University. That's opencv.org/university. If you're ready to break into AI, become a certified AI professional with our expertly curated computer vision and deep learning courses designed to take you from beginner to mastery in AI. There's even some free courses. You can take the VLM Bootcamp, the PyTorch Bootcamp, OpenCV Bootcamp, TensorFlow Bootcamp, Python for Beginners, absolutely free. Now, these are much shorter, compressed, just a few hours courses compared to the much more in-depth semester-long, if not longer, courses such as Mastering OpenCV with Python, Deep Learning with PyTorch, Computer Vision and Deep Learning Applications, etc. Any thoughts? You want to give the folks a quick pitch about OpenCV University, Doc?
Yeah, so OpenCV University is basically a collection of courses that bring you from complete beginner to mastery in computer vision. So two of our courses, fundamentals of computer vision and image processing, and one of the deep learning courses. There are two flavors of our deep learning course. One is in PyTorch, the other is in TensorFlow. If you do two of these courses, you can be very certain that you have a lot of skills necessary to start a career in AI. So of course, welcome to our course. Results will vary, but people from our courses, they have started companies raising $7-8 million. There are people who they're now working with Tesla. So all kinds of success stories we have. You can go and check them out on the website itself. But the courses, they are for serious people, right? For people who want to start a career in computer vision, and not just, I want to do something in 7 days. No, so we have the free courses you can do very quickly, but the paid courses, these are for people who are really serious about a career in computer vision and AI. So check them out. And if you are one of those people, this would be, I cannot recommend it more, right? It is, we put our heart and soul into building these courses, very high quality courses.
Yes, absolutely. Please check out OpenCV University. Okay, let's see here. I'm going to take off our OpenCVU thingy, and I'm going to go ahead and start with today's trivia question. Please, if you have won in the last couple of months, do not answer and give someone else a chance to win. Also, you can answer anywhere that you're watching in the chat. Please use the if you're on Zoom, make sure your messages are sent to everyone so we can make sure that the it's visible to the public. I think the last couple of weeks we've had some YouTube winners, so Twitch, Zoom, get out there, get at it. So today we've talked quite a bit about a bunch of algorithms and how they work, specifically one called VGGT. Which university is VGGT associated with? Which university is VGGT associated with? Answer in the chat to win. Ooh, we got a few already. Let's see here.
Yeah.
Who was first? Over on Zoom, it looks like Borna Farnad. The answer we're looking for was Oxford. We could have been real tough about it and made you use the full name, but I think
it's fine. Yeah.
Oxford is good enough. A few folks on Zoom got this one. We also had Matt over on YouTube, was just a little bit late, a little bit later. So congratulations to Bornad. Please send one email to me. That's phil@opencv.org to get your prize. Congratulations as well. Go ahead and remove our trivia thingy here. And so we've got a whole bunch of questions. We definitely do not have time to answer all of them, but we're going to answer a couple of them here. So let me go ahead and pull them up. Lots of questions here today. So the first one we'll go with here is Matt Bay, who asked, I'm more curious how well it works with, quote, distractors, and, quote, what's the tolerance for material changes between two frames?
Yep. So the experiment that we did with the lighting changes so we completely changed the lighting from yellow to a blue lighting, and also moved us around some objects. We didn't see any degradation in camera pose prediction quality. If there is a bigger object in the scene, that might be the center of it, right? And that is like changing continuously, maybe like a TV screen which on something is playing, but which is the main part of the scene, that might degrade the quality. But with changes in the smaller objects or even markers or lighting changes, we also moved the chairs a little bit that were in the scene. We didn't see any issues.
So I'm guessing that, if you change a painting in a room, right, a big painting, then you may see problems. If you change the table, if there is a table like in a meeting room, you're changing the table, maybe you can see some problems, right? But if you're moving small objects like, let's say, markers and things like that, then it's going to be stable.
Yeah. Even chairs as well. So like chairs slightly here and there, we didn't see any issues.
All right, good to hear. Next question over on Zoom, we have Leslie Ann asks, sorry if this was explained earlier, but are there examples of areas with variable elevation like a hilly area? I think, this is part of why we're focusing on indoor for this one, but correct me if I'm wrong there, Gursimar.
Yeah, so we have done most of our experiments indoors till now with this, because that was our focus for the application. But the results that the authors have provided from the outdoors, they include hilly areas, they include, as we saw one of the amphitheater example, right? So at least from the what we have from the authors, it works pretty well.
Okay. Thanks for that. A couple more here. We answered this one, but I'd like to highlight it and talk a bit more about it because I mean, currently the answer is, as is often the case, it depends. But I think in this case, the answer is no, but. So Cosmic Amusement on YouTube asks, can this work in real time?
So the inference part of it, the not the training obviously, right, but the inference where you want to do the localization, that on a 5090 GPU currently, the code that we have is around 250 milliseconds, right? So we can for some applications we can say it's near real time, but there is scope of optimizations there as well, right? So maybe up to 100 milliseconds or 100 150 milliseconds, and that is something we are also working on internally to reduce that time or get similar time at least on a Jetson.
Yeah, and that makes sense. I mean, hey, 250 milliseconds, nothing to sneeze at. It's not quite real time, but still pretty damn fast.
Yeah.
Pretty damn fast. Let's see what else we got here. Another question from Daniel over on LinkedIn. Did you use these Aruko markers during training?
So we did not use those Aruko markers specifically during training. Without Aruko markers, it worked pretty well. It's just that because we have been trying all the classical methods and all the deep learning methods before this, right, which were not being robust. So these Aruko markers were just there when we like collected the data, right? But the Aruko markers, role of the Aruko markers, which we propose is just for stitching different scenes, right? They are not there for the camera pose accuracy, and that we have seen when we remove the markers from the room while doing the queries, it still works pretty well. If there's a very complex scene we don't have features, definitely Aruko markers will help in this case as well.
Phil, you're on mute if you're speaking.
Just mumbling to myself.
Okay.
Just looking over. We got a few more questions here. We'll do a couple more before we let people go. People are asking more questions at the end, which is always what happens. Over here, we've got on YouTube asks, did you use a high frame rate camera here? Also, when stitching the two rooms, was that a manual process or was this automated in some way?
So we have just used an iPhone, so 30 FPS standard recording at a 1080p resolution. That's what we did, and we like the input is not the complete resolution; it is a lower resolution. I think 640 cross 640 image. And for the stitching for the two rooms, we have it's an automated pipeline. That's why we use the Ruko markers there, because it can be detected easily using other algorithms, and then the alignment can be done automatically.
But the frame rate, just to ultimately only 150 frames were chosen, right? So the frame
Yes.
rate actually doesn't matter because we are subsampling so much, right? Only 150 frames are used for that reconstruction.
Yeah, it only might matter in the case if you are getting blurry frames. Like, so if your scanning or motion is fast, right, you can use a higher FPS camera and make sure you don't get blurry frames.
Yeah.
Yes, that's true. There's other sacrifices, of course, usually with higher FPS. There's other trade-offs that you generally have to make unless you
Noise.
have infinite money, which probably most of us do not. One more here. We've got also from Leslie Ann over on Zoom. How well does VGGT do on agricultural images, like say in dense forested areas with vegetation?
So I think that we have already talked about, right, about similar to the hilly areas, right? Most of our experiments have been indoors, and that was our today's focus. But there are some outputs from authors which you can check out.
Yeah.
Yeah. Okay. I think those are most of the questions we've got here today.
It almost sounds like veggie nut, right? So,
VeggieNet.
so bad.
Hey, you got the new product. Yeah, I mean that's we have a couple more questions, but folks, we're running out of time here. If you had a question that did not get answered, please send it to newsletter@opencv.org, and we'll do our best to make sure that gets answered. And we will, with Gursimar's permission, drop these slides in the YouTube show notes.
Yeah.
So look for those after you'll send an update on Friday for the OpenCV newsletter, and we'll make sure those notes are in there.
All right.
Um, Thanks, Gursimar. If folks want to follow you around on the wide world of Al Gore's internet, how can they do that? What's the best place to check you out?
I think I just have a LinkedIn profile, so you can search me on LinkedIn.
All right, yeah, go to Big Vision and find Gursimar on LinkedIn. Doc, you want to take us home?
Yeah, thank you so much, Gursimar. This I'm glad the project is coming along really nicely. This is an internal project of OpenCV, and we are really glad. For people who watched this episode, right? We covered a lot of things. I want to make sure that there are few things that you remember from this episode, which can be very useful, even if you're not building the exact same application. The first thing is obviously the core was VGGT. So that's one thing. If you do not know about solve PNP, look it up. There is a article we have written on Learn OpenCV as well. Solve PNP is very useful. If you have been using features like orb features or surf or sift features, that time is over, right? Those were the features from the last decade. So do not use them. Use modern features like Superpoint, and then look up Superpoint Superglue that you can use for feature matching if you have not already started using those. So yeah, and also look up Master and Duster if you are interested in some of these techniques. And finally, we have Gaussian splat, which is a technique for novel view synthesis. So some of these things, if you learn, even if you do not use the exact same application, you will use some of these. If you're interested in anything related to 3D, you will find these very useful. And finally, there is A0 also in the same category as Master, Duster, etc. So we'll put them in these things in the show notes. So individually also these resources are very, very useful. All right. So that's all I wanted to cover. And thank you so much for joining us. It's always a pleasure to be here every Thursday and provide some value to you, and also interact with our audience. Thank you, Gursimar, for this excellent presentation, and thank you, Phil, as always, for organizing the show. Nothing went wrong.
Yeah, so far there's still time, but yes, thanks everybody for watching. We wouldn't do the show if you didn't watch it. We'll be back next week with our friend Jody Burchell from PyCharm to talk about some more of the latest and greatest with the official Python IDE of OpenCV, PyCharm from JetBrains. But until then, take care of yourselves out there. Take care of somebody else if you can, and let's go Cubs. Adios.